attention, I'm sure, as we close the end of the conference. The topic that I want to talk about today is a topic that has been central to philosophers of science understanding about the relationship between different theories. And it's an idea which was first expounded in forceful ways by both Kuhn and Feyerabend in 1962. They both had ideas about an idea about how the conceptual frameworks of different theories, especially successive theories in science, can be incommensurable from one another. And the way that they wish to illustrate, substantiate that claim is by providing specific examples. And one of the sort of specific examples that they provided, and which has kind of been absorbed into apparently philosophers' common knowledge that we learn at our mother's knee, is that the best example that we have for that is the concept of mass in Newtonian physics and the concept of mass in relativistic physics. Here is Feyerabend on this. He says, in classical, pre-relativistic physics, the concept of mass was absolute in the sense that the mass of a system is not influenced by its motion in the coordinate system chosen. Within relativity, however, mass has become a relational concept whose specification is incomplete without indication of the coordinate system to which spatiotemporal descriptions are all to be referred. The basic idea here is that Feyerabend wants to give evidence for his claim of incommensurability by showing how the concepts of mass in the two frameworks have different properties. And it's a facto because they have different properties, they can't be referring to the same thing. And here's Kuhn, providing similar sorts of reasoning, comparing the properties of mass in the two theories. He says, Newtonian mass is conserved. Einsteinian mass is convertible with energy. Only at low relative velocities may the two be measured in the same way, and even then, they must not be conceived to be the same. So what exactly are they talking about? I think a common way, and a very simple way of illustrating that, is they're thinking about the standard free momentum of a particle in Newtonian physics is just given by the product of the particle's mass with its velocities measured in some reference frame. The mass is a constant. Now, if we look at the comparable formula for relativistic physics, for relativistic mechanics, and we take it that the form of the momentum equation should be the same, we're forced, on pain of contradiction, to realize that the term m here, appearing in the equation, has to be proportional to the relativistic gamma factor. That is, a constant, m0, times the gamma factor, which is, of course, dependent upon the velocity. This is what Feyerabend was talking about when he was saying that the mass is frame dependent because the measurement of the particle's velocity is frame dependent. Now, Feyerabend tries to anticipate an objection, right, saying that, oh, we should be looking at m0 as the relevant mass concept, the representation of the mass concept in special relativity. So this quantity, the rest mass, he says, is defined from frame-dependent relativistic mass, right? Among all of the frame-dependent values of mass, it is the minimum, in particular, the value taken on in a frame which is co-living with the particle. So I think these sorts of ideas have been so much absorbed into the philosophy of science literature, and no matter what controversy people find about examples of commensurability, they always think that the example of mass is the one that is the strongest, that has the strongest evidence for it. And this has a lot of consequences. In particular, it shows that Newtonian and special relativistic mechanics remain incommensurable, at least due to their differing concepts of mass. And that because of this incommensurability, no reductive or otherwise explanatory relationship can really exist between them. So exhibiting any sort of correspondence limit between the theories, therefore, must remain a purely formal procedure, one which can connect up the symbolic mathematics of the two theories, but which does not connect the concepts of the theories. What my claim today is that one ought to resist all of these claims. In particular, I want to do so constructively. One can exhibit a common four-dimensional formalism for both classical and relativistic particle mechanics. This formalism has a single functional role for mass, but the way that that role is implemented in the two space-times is not due to different concepts of mass, but rather the way that that function is implemented in different space-time structures. To give you a metaphor, in mammals, one can have appendages which are hands, and one can have appendages which are like flippers. Now you could say, hands and flippers, look, one you've got digits, the other you don't, completely different, right? They have different properties. But if you understand the two functionally, you see that they're playing the same functional role in the context of motion, locomotion, in animals. And the way that the differing properties that hands and flippers have has to do with the context in which they've evolved, on land or on water. So this is a bit of a metaphor, but I think take it to be suggestive, because the differing apparent properties of mass don't have to do so much with different concepts of mass, but the way that the very same concept is implemented in different spatiotemporal contexts. So what I'm going to do for the rest of the talk is just describe what this framework theory is. It's going to be a modification of a framework that was developed by the physicist Jürgen Ehlers, and it describes the common structure of classical and relativistic spacetimes and describes particle collisions within that. Then relativistic mechanics and classical mechanics come out as specializations, particular cases of this general frame theory. I'm not going to have a lot of time to respond to many objections. Actually, many of them have to do with issues that Kevin was just talking about. So I'm going to bracket a few of them and say only a couple of responses to objections in passing. Okay, let's get started. Well, okay, let's not get started. I first want to say what I'm not doing. I'm not giving a systematic response to the incommensurability literature or to the mass energy equivalence literature. Kevin has done that nicely. I'm not claiming to advance a new formalism. I think all of the ingredients that I'm using have been developed in the physics literature before, but not put together for this particular purpose. And finally, I'm not contesting the historical claim of incommensurability. It may well be the case that if one wants to understand incommensurability in the appropriate historical context, that the relevant actors at the time really did think that they were using different concepts. Rather, the perspective that I want to take today is that based on the best available theoretical ideas and methods in mathematics that we have, can we understand the best way of understanding the relationship between the two? And in particular, I think we can do that in a way that shows that the two theories of mechanics are much, 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 much closer than we thought that they were. Okay, so here is the common structure. The common space-time structure. We have a smooth manifold of events. These are point coincidences. We have a symmetric temporal metric and a symmetric spatial metric. The temporal metric is going to determine the lengths, the durations of certain types of curves. The spatial metric is going to determine the spatial distances determined by different sorts of curves. And the way that it's going to do that is by integrating certain tangent vectors to those curves in a way that I'll describe on the next slide. But before I do that, there's a few more elements that are important. Another is we're going to have a connection. It's going to be torsion-free and it's going to be flat. I'm going to be working, in other words, in special relativity and completely without gravitation, although I'll have a word to say about the generalization to the gravitational case at the end. Now, this connection is going to be compatible with both of the metrics. This compatibility condition says that the notion of change of various quantities that you can get through the temporal metric and the spatial metric is going to agree with this connection. In other words, if you have a particular temporal quantity that is defined along a curve, you can use the temporal metric to see how that quantity, right, as a real value, changes along that curve. What this says is that if the temporal metric thinks that that quantity remains the same, then the connection is also going to agree that it remains the same. And similarly with spatial quantities. Now, the last condition here, which is quite suggestively called the causality condition, instigates a certain compatibility between the spatial and the temporal metrics. What it does is it requires, in a very particular sense, that the spatial directions and the temporal directions don't overlap with one another. So a spatial direction and a temporal direction is going to be an instantaneous direction in the manifold of events at a particular point. Now what's really important here is that there's a constant here, kappa, which we may suggestively call the causality constant. Now, depending on the value of kappa, we're going to get one of two cases. If kappa is going to equal 0, it turns out that the space-time structure, the temporal and spatial metrics, are going to fit together in exactly the way that we have in Newtonian spacetime, really Galilean spacetime, but let's ignore those differences for now. If kappa is going to be a positive value, meanwhile, we get the structure of Minkowski spacetime. This is a diagram of this sort of idea. So for kappa equal to 0, the spatial directions, or when they're properly extended, are going to give us leaves of space. And the temporal direction, which is going to be orthogonal to that, tells you how to go from one spatial leaf to another. Now, if kappa is going to be greater than 0, then even though we still have a division of spatial and temporal directions, we no longer have a division that gives us spatial slices. Rather, we have the familiar null cone, where an instantaneous direction that lies inside the cone is going to indicate a time-like direction. One outside is going to be a space-like direction, and one on the boundary is going to be null. Let me be a little bit more precise about that, how that terminology fits in with every model of the theory, and not just those that are specializations to relativity theory. So here we have our manifold, right? This is our general manifold. Let's consider some curve or other, gamma, in the manifold. A particular point on the curve is going to have associated with it a tangent vector for that curve. And we can classify the tangent vectors in exactly the way that I mentioned before. To be more precise about it, we'll say that a tangent vector is going to be time-like when the temporal metric assigns it a positive length. It's going to be space-like when the spatial metric assigns it a positive length. You have to do a little bit of fiddly business with the mathematics in order to get that right, but I'm going to skip over it because it's not very interesting. And finally, it's going to be null when the vector is neither time-like nor space-like. Now, how many null vectors we have is going to depend on the value of kappa. If kappa equals 0, so that we have Galilean spacetime, the only null vector is going to be the 0 vector. And of course, that's not the tangent vector to any curve. So through this particular definition, you get a classification of curves by their associated tangent vectors. So a curve is going to be time-like, just in case its tangent vector is everywhere time-like, space-like if it's every space-like, and null when it's everywhere null. Tangent vector is everywhere null. Okay, so now we can consider continuous, piecewise smooth, time-like, or null curves that are within that manifold. These, we're going to postulate, are going to represent the possible trajectories of particles. Now, the geodesics, according to the connection that's been provided, are going to represent the free particles, those that are not undergoing any forces. Now here's the crucial part where we add in the bit that's going to allow us to do very simple particle mechanics, just collisions. We're going to associate with every particle a momentum, form momentum that is co-directed with its forward velocity. And finally, we're going to define the particle's mass as the temporal magnitude of that forward velocity. Now, one of the things you'll notice is that for time-like particles, that is those who have a time-like trajectory, this quantity is always going to be positive, and for particles that have a null trajectory, this quantity is always going to be 0. So the functional role, in other words, of mass here is the temporal length, right, of this particular 4-vector momentum. So now we can talk about interactions or collisions. These are going to be the intersections of at least 2 particle world lines. So if you have particles labeled by alpha that are undergoing interaction, that is, they're undergoing a collision at one of these points, it could look like this. There's many other topologies that the intersecting world lines could have. And you have particles labeled by alpha prime resulting, we're going to require conservation of form momentum. The ingoing form momentum is going to be equal to the outgoing form momentum. And this equation makes sense because it is being applied only at the point of interaction, so all of the form momentum, right, live in the same tangent space. Okay, that's all of the common structure. So what are the differences between the 2 specializations in this common framework theory for particle mechanics? Well, it really just has to come down to differences between the value of kappa. If kappa equals 0, the time-like metric, the temporal metric and the spatial metric take on a particular degenerate signature, and we only have time-like particles. In the relativistic case, where kappa is going to be positive, in particular we usually set it to the inverse square of the speed of light, the temporal metric is just going to be the usual Lorentz metric. And then the spatial metric is just going to be proportional to the inverse Lorentz metric. And in this case, we have null and time-like particles. Okay. So here is a kind of summary of everything that I've said so far. You'll notice that in a lot of the rows, right, the entries are exactly the same. Right? In every case, we have a manifold. In every case, we have a symmetric temporal metric, and although it has different signatures in the two cases, and similarly with the spatial metric, the derivative is always going to be torsion-free and flat. We always have the compatibility condition. And then finally, the big difference is for the space-time structure, this causality condition is specialized for two values, 0 or positive. But this results in us having particles in the one case that are only time-like, here that are time-like or null. And finally, the conservation condition is the same across each case. How much time do I have?
We started about on time, so we've got about 20 minutes.
All right, so I'll finish up quickly then.
Engrossed in the tool.
All right. Consider an observer now.
You've had 16 and a half.
16, okay, all right, that's better. Good. So now let's use this framework for particle mechanics to recover the usual laws for collisions. So let's consider an observer with tangent vector v who's interested in measuring the properties of a particle that has form momentum p. That observer is going to decompose that form momentum into two components. The first component, which is going to be time-like and parallel, right, to the observer's form velocity, has a particular magnitude to it. It turns out that depending on the structure of the temporal metric, that magnitude is one of two things. In the Newtonian case, right, the case where kappa equals 0, this component is extensionally equivalent to the mass. And in the case of relativity theory, it's extensionally equivalent to the energy that the observer will measure for the particle. And the second component here is going to be vary from particle to particle. It's going to be the 3 momentum. And it's going to be the 3 momentum in both specializations of the theory. Now, the nice thing about this is that conservation of form momentum immediately entails conservation of these components. So we immediately have conservation of 3 momentum in both of the relativistic and non-relativistic cases, and the conservation of the time-like component, that is time-like relative to the observer component of the form momentum in each of the cases, yields either conservation of mass or conservation of energy. Okay, so that's kind of the story. In both Newtonian and special relativistic mechanics, mass is the magnitude of the form momentum as determined by the temporal metric. The functional role that it plays is determining a particular component or quantity of it that plays a special role in the form momentum conservation. But the way that that quantity is understood and how it's related to other quantities in the theory depend on the structure of the temporal metric, but not on the differing structure of different concepts of mass. In particular, all of the differences, right, from the two specializations of this frame theory of the concept of mass arise from how the same function is implemented in different space-time structures. So what about Feyerabend's example? So when we come back to Feyerabend's argument in his example, we see that frame-dependent mass doesn't play the same functional role that the analogous quantity would in the Newtonian physics. The relationship between them is unfortunately only syntactic. It only bears an orthographic similarity to Newtonian mass, but not a functional similarity. Even though they are written down in the same sort of way, we ought not to be misled. They're not playing the same function. Okay, so what have I done? I've exhibited a 4-dimensional framework of concepts for both classical and relativistic mechanics. whose specializations into the two differ only by a single parameter. In particular, mass takes on a single functional role, and differences in how this function are realized are due to differences in space-time structure rather than differences in the mass concept. In further work, I'd like to extend this to the gravitational setting. Depend on some details. This requires a small amount of difficulty or is trivial. I can talk about that more if you want. Others I want to prove more rigorously, or develop a rigorous argument for showing the correspondence limit between the two theories. I think this is helpful in solidifying the evidence that the concept of mass is really playing the same functional role, because it would show how the same functional concept is related in limiting cases to the outcomes of concrete experiments, if this limiting relationship is understood in terms of approximation of observables. And finally, I'd like to think about and ask your opinion about whether there are other barriers to commensurability between the two theories. Thank you.
So Sam, one thing that's going on here is that you're individuating and generating commensurability on functional grounds.
That's right.
Right? Rather than aiming for some kind of metaphysical commensurability or commensurability in terms of meaningfulness. You're allowing for a broad range of functions, presumably the explanatory role with the objects, but this has a pragmatic feel to it. And I just wanted to mention this because it's that's part of what's doing the work here, is getting commensurability on functional grounds rather than on some kind of metaphysical or semantic grounds.
Yeah, that's right, that's right. And I think to solidify the pragmatic aspects in the way that it relates to comparison of different sorts of results of experiments, I have to say more detail about that, but one only has 20 minutes. Wayne?
So I don't want to be an advocate for incommensurability or let any at all for comfort to fire off, but I think that you're a little too quick in dismissing, in the second to last slide, in saying that this, the frame-dependent notion of mass doesn't play any functional role. Because you picked out one functional role that the Newtonian mass plays. But there's another functional role that it plays, which is basically as inertia, a measure of how hard it is, how much force I have to apply to produce a certain acceleration. And if I'm looking for what what takes plays the functional role in relativity, well, it is the velocity dependent mass. Like if I'm designing a particle accelerator and I want to know how much force I have to apply to speed something up, then that's the concept I want to use. Yeah.
So I think it depends.
Okay.
So I've tried to write a 4-vector equation here, and I've tried to write a 3-vector equation here.
Right.
Now, if you had picked a frame of reference, which is extremely convenient, say the lab reference frame, because you're doing particle accelerator experiments, and this is like totally well-defined and extremely convenient, then you're going to be interested in this sort of equation because you've entered in a lot of extra data. But there's an analog to Newton's equation, right, which is the 4-vector version. And in this 4-vector version, we do have a functional role played by the mass that I'm talking about using in relation to the form momentum. The problem, I think, with those sorts of cases where we want to insist that this velocity-dependent mass is playing the appropriate functional role is that one ends up having to explain away certain sorts of differences between the Newtonian theory version of the theory and the relativistic version. So in particular, if we want to explain the the functional what is the functional analog of the mass, the velocity dependent mass here, we have to do a lot more tricks to explain away why the similar sort of concept arises in a different sort of way in the Newtonian version. I can't give a full story here because it takes a little bit of time, but it's a good question, but I think that it can be answered.
Okay. Chris?
Actually, it's the same as Wayne.
Okay. Harvey?
Well, I just want to, just to add to that point, in the corollary 5 in Principia, Newton derives the relativity principle from the laws of motion. And in doing so, he presupposes that mass and forces are velocity independent. Because without those assumptions, you can't get out the Galilean covariance of Newtonian equations of motion. And it seems like an afterthought. It seems like you could have a perfectly good Newtonian, the laws of Newtonian mechanics with velocity-dependent masses. It just wouldn't satisfy the relativity principle. So again, it's not really an intrinsic property. In that sense, it's not really an intrinsic property of the mass that is velocity-independent.
Yeah, so maybe I should say a little bit about my methodology here. So there's two views about incommensurability that you could have. One view about incommensurability that you could have is that in order to disprove, in order to show commensurability, you have to show that every possible identification of concepts is commensurable. Another way of approaching the methodological question is showing that there's one way of understanding the relationship between the theories where the concepts are commensurable. For better or for worse, I've taken this latter approach. I think that it's helpful to exhibit a way of understanding how the theories are similar to one another, even if we can come up with other theories that in some sense are makes similar or the same predictions that use other concepts.
Two very short historical questions. One is that I have the impression, if I maybe it's wrong, that when I studied 40 years ago physics, many books used mass in relativity to mean the velocity dependent one and zero gamma. While this is not true anymore, and most books just call mass and mass. The second question is about the notion of commensurability, incommensurability in Kuhn. Is it true that it emerged from his early work on more on this birth of quantum mechanics? At the beginning, he simply meant the fact that a scientist lose track of what he himself meant before having an idea, and it came from his realization that Bohr accounts different work from what he was.
Regarding the first question, I think that there is some variability in textbook treatments from era to era and from inclination of author to inclination of author, and I haven't done a systematic examination of them, so I can't really say much more about it. Regarding the second, I'm hesitant to undergo Kuhn exegesis, in part because I think there's quite a bit of evidence that there are many facets to Kuhn, all of which probably can't all be viewed at once. In fact, I think there's, to put it another way, right, I think that there's aspects of Kuhn that are incommensurable with one another. So some of the things that Kuhn said, I think, are quite, perhaps quite inspired by these sorts of studies that he made, but other things that he said later on don't seem as much related to it. And I'm afraid I can't say much more than that.
But it is true, he wrote the black body incommensurability is false stuff.
Can you say that
again?
again?
About black body, about the black body discontinuity. I don't know, he did do work on Bohr, right? That's what you're thinking about. But I don't know. Okay. We have 40 seconds left if there's something urgent, but I think let's call it a day and say thanks.